Every day, all around us, we listen to music, whether it's in places like restaurants, at events like parties or family gatherings, or even at home. I'd like you to think of your favorite song. Maybe it's a pop song, a movie soundtrack, or a piece of classical music. What if I told you that behind every beat in this song, behind every melody that you hum along to these songs, and every chord makes these songs so deep and beautiful is something you probably weren't thinking about at all: mathematics. Music isn't just inspired by math, it's built on it. More, more than 2,500 years ago, the ancient Greek mathematician Pythagoras noticed something remarkable. By plucking strings of different lengths, he discovered that beautiful musical soundtracks were created by simple numerical ratios. This discovery showed, for the first time, that music and mathematics are deeply connected. Thousands of years later, we still use these mathematical ideas every time we create or listen to music.
Hello, my name is Ahmed Arman Ibrahim.
Today, I will present to you Finding Math in Music. First, let's look over what we will be going over today. First, we will be looking at an introduction to music and mathematics and their topics. Then, we will move on to rhythm and how it's connected to mathematics, including notes, their length, and time signatures. Then, we will move on to the physics of sound. After that, we will study music theory in 12 tone temperament and patterns in geometry found in maths and music. Then, we will be looking at the Fibonacci sequence and golden ratio. So, let's get on with the presentation. Even though at first music and mathematics seem completely different, both are built on recognizing patterns and relationships. Rhythm depends on counting and fractions, harmony depends on ratios, scales are created using exponential relationships, and melodies often repeat or transform in predictable ways. Even when musicians are not consciously thinking about mathematics, they are constantly using these ideas while reading sheet music, keeping time, and performing their pieces. Mathematics provides the framework that allows music to be organized, understood, and shared across cultures. Let's look into how mathematics is found in rhythm. One of the simplest ways mathematics appears in music is through rhythm. Every musical note represents a fraction of time. A whole note lasts for one complete unit, a half note lasts one half as long, a quarter note lasts one fourth as long, and this pattern continues with eighth and 16th notes. For example, if a whole note lasts 4 seconds, then a half note lasts 2 seconds, a quarter note lasts 1 second, and an eighth note lasts half a second. This means musicians are constantly dividing time into equal parts. Although they may not think about solving fractions while performing, their sense of rhythm depends on these mathematical relationships. Any
Time signatures act like mathematical instructions for a piece of music. They tell musicians how to organize the beats into measures. The top number indicates how many beats are in each measure, while the bottom number tells us which note receives one beat. For example, in 4/4 time, there are 4 quarter note beats in every measure.
music piece in any time signature with the same tempo will always match up perfectly in times of rhythm if the time signatures have the same bottom number and one of the time signatures is a multiple of the other.
Let's look at an example.
In addition to this, two different time signatures that are equivalent to each other in fraction form will always match up with each other. For example, 3/4 and 6/8 time. Lastly, you can find the ratios between the time signatures in fraction form, and if their tempos are in the same ratio, they will always have the same starting beat. This will create interesting polyrhythms, for example, 5/4 and 7/8 time at a tempo ratio of 10 to 7. Now, let's go into the physics found in math and music. Every musical note is a sound wave vibrating through the air. The number of vibrations each second is called the frequency, measured in hertz. A higher frequency produces a higher pitch. For example, the note A, right above middle C, has a standard frequency of 440 Hz. The A one octave higher vibrates at 880 Hz, exactly double the frequency. This creates a simple ratio of 2 to 1. Other harmonious intervals are also based on simple numerical ratios. For example, the perfect fifth, which has a ratio of 3 to 2, is a very common musical interval found in pieces. These simple relationships explain why certain combinations of notes sound pleasing together, while others are dissonant. The musical intervals include unison at 0 semitones, a minor second at 1 semitone, a major second at 2 semitones, a minor third at 3 semitones, a major third at 4 semitones, a perfect fourth at 5 semitones, a tritone or an augmented fourth at 6 semitones, a perfect fifth at 7 semitones, a minor sixth at 8 semitones, a major sixth at 9 semitones, a minor seventh at 10 semitones, a major seventh at 11 semitones, and an octave at 12 semitones. In most cases when making music, the simpler the ratio, the more harmonious the sound is. A cent is a logarithmic unit used to measure the size of musical intervals. There are exactly 100 cents in one semitone and 1200 cents in a full octave. A semitone is a standard half step, like the distance between two adjacent piano keys on a keyboard. All chords in music are constructed by putting together all these different intervals between notes. Any major chord is constructed by finding a root note, then adding the major third and perfect fifth. There are also many other chords that are constructed by modifying existing chords and or using different intervals. Let's go into equal 12-tone temperament in music. Modern Western music uses a system called equal temperament, which divides one octave into 12 equal semitones. Interestingly, these notes are not equally spaced by adding the same number of hertz. Instead, each note is found by multiplying the previous frequency by the 12th root of 2. This relationship can be written as Fn equals F0 times 2 to the power of n over 12, where F0 is the starting frequency and n represents the number of semitones. Although the formula may look complicated, its purpose is very simple. It allows musicians to play in any key while keeping every note reasonably in tune, with 12 equal semitones. For example, A in the 4th octave is 440 Hz. A sharp in the 4th octave or B flat in the 4th octave is 440 times 2 to the 1 over 12 in power, which is approximately equal to 466.16 Hz. An A note in the 5th octave is equal to 440 times 2, which is equal to 880 Hz. Each note is found by multiplying by about 1.05946, not by adding a fixed number. Music is also filled with countless patterns that resemble the transformations we study in mathematical geometry. A composer may repeat a melody exactly as it first appeared, creating repetition in a piece, but they might also shift the same melody higher or lower. This is a transformation similar to geometric translation. Sometimes, melodies are inverted so that every upward movement becomes downward, creating a reflection. They can even be played backwards, a technique known as retrograde. These transformations, with heavy mathematical influence, help composers create musical ideas while also maintaining unity throughout a music piece. They also make music easier for listeners to recognize and remember, because our brains naturally enjoy these kind of patterns in music. Mathematics can appear in music in even more surprising ways. The Fibonacci sequence, which begins with 1, 1, 2, 3, 5, 8, and 13, appears often throughout nature, from flower petals to seashells. This is closely related to the golden ratio, which is approximately 1.618, which has long been associated with balance and beauty. Some music analysts have suggested that the climaxes of certain compositions occur very close to the golden ratio, creating a satisfying sense of proportion. Although scholars continue to debate whether composers intentionally use this relationship, the connection reminds us that mathematical ideas about balance and symmetry can also influence artistic design. That will be all for today. Thank you for listening to my presentation.